Welcome to the first physics class for the students of class 12. Our topic is Introduction to Electric Charges and Fields. Before we start our class, let's do one experiment. I think you all remember we did this as a kid. Here I have taken a small amount of paper which is cut into small pieces, and I have taken a scale and I have rubbed it in my hair. And now what I'll do is I'll bring it near to the paper. What we see here is this paper get attracted to the scale and stick to the scale, and it doesn't fall down. See? Okay, we'll explain this experiment why it is happening. Let's start our class. Okay, before starting this chapter, let's start with the explanation of the activity that we just saw. Okay, so here in this activity, what we have done was we had taken some small papers, right? And when we brought the rubbed scale near it, we saw that the papers sticks to the scale and it doesn't fall down. That means it remains stuck to the scale. Okay, what is our day-to-day experience? Our day-to-day experience is anything object which is placed here above the surface of the earth, it will fall down because of the gravitational pull, right? So likewise, if we take this papers, if we carry it with the help of our hand and we release it, what we see is it will fall down because of the gravitational pull, gravitational force of attraction. This is one of the fundamental force which is acting in the matter. Okay, and what is the reason of this gravitational pull? Gravitational pull force is due to its mass. More is the mass, more will be the gravitational pull. As the earth is made up of huge mass, that's why the object placed near the surface of the earth, they experience gravitational pull and they fall down. Okay, so here in our case what we see is against gravity, these papers, they are sticking to the scale. That means there is some another force which is acting between this paper and the scale. Okay, that second type of force is acting is called electrostatic force. Okay, now what is the source of this electrostatic force? Here the scale acquires the ability to attract this paper because we are rubbing it in my hair. In this case, I have rubbed it in my hair, and after that it acquires the ability to attract this papers. Okay, so what happens when I rub this scale in my hair? It acquires electric charges. Okay, so here when a body has developed electric charge, some kind of force develops in it. That force is called electrostatic force. Okay, when the body has electric charge, it acquires the ability to attract another matter near it because there are electrostatic forces acting among them. Am I clear? Okay, so now this is the definition of electric charge. It is the intrinsic property of matter. Intrinsic property means it is already present inside the matter, but it is visible when I rub this scale in my hair. Okay, it is like when we see deep inside the sea water, the water is calm. Okay, and the water is not visible when we are deep inside it. Okay, water will be visible only when we disturb it, when the waves are formed. Okay, likewise inside the matter charges are present but we cannot see it. Okay, and the net charge is 0. Okay, but when we disturb it, it appears. Okay, likewise, that's why it is called the intrinsic property of matter. Okay, which gives the the body the ability to attract another matter which is placed near it. Hope I am clear till here. Okay, so electric charge is the source of electrostatic force. Okay, second example here as shown in the figure. What we have done here is we have taken a balloon, and when it is rubbed with the sweater, it acquires the ability to attract the hair. That means it is acquiring charge, because of which it is having the ability to attract the hair, and the force that is acting in this case is called electrostatic force. Okay, from the name itself, it is what? Electrostatic force. That means when the charges are at rest, we are considering charges are at rest, it has the force acting in it is called electrostatic force. Okay, now how many kinds of charges are there? There are two kinds of charges, positive and negative charge. Okay, here in the first activity that we had seen in the plastic, when we rub it with the hair, the plastic acquires negative charge. Okay, so likewise many experiments were done, and it was found that different material acquires different charge, positive or negative, depending on the substance with which it is rubbed with. Okay, and those substances were placed in the series that is called electrostatic series. Okay, now how to find out which body acquires positive charge or negative charge? Okay, so for that we'll take some example. If we take glass with silk, glass rod with silk, we are taking a glass rod, we are rubbing it with the silk cloth. Okay, here glass is above the silk in the series. When glass is rubbed with the silk, it acquires positive charge. Okay, so from the series what we can see is if the object is above, okay, then that object will acquire positive charge. Okay, clear? That means here silk is below the glass, that means the silk cloth will acquire negative charge and glass rod will acquire positive charge. Okay, so different experiments were done, and it was found that here in the masses, what we have studied is between the masses gravitational forces act, and these gravitational forces are attractive. Okay, but here in our case different experiments have shown that these charges that develop in the body, they are both, sometimes the forces develop, they are both attractive and repulsive. Okay, so here suppose this is the glass rod, both are the glass rod rubbed with the silk cloth. Okay, so this glass rod acquires positive charge, and when it was taken and it was tied here with this silk thread, okay, and when they were brought together, it was seen that they moved away from each other. That means from here what we can conclude, when the charges are present in both the bodies, they are same, they will repel each other. Okay, they will move away from each other. Okay, likewise second experiment was done with the plastic rod. Okay, and this plastic rod was rubbed with a woolen cloth. Okay, and it acquired negative charge. When it was brought together and it was tied with the threads which was free to move, okay, and it was seen that these two plastic rods, they moved away from each other, same as before. Okay, when two glass rods were brought together, charged glass rods, they moved away, and again when we brought two plastic rods, then again they moved away. That means when they have same kind of charge developed, they will repel. That is, from that we can conclude like charges repel each other. Okay, and then another experiment we have seen, for example, if we take glass rod with the positive charge and plastic rod with the negative charge, and it was tied with a thread, and it was found that they moved towards each other. That means this opposite charges are attracting each other. Okay, so we have seen here by these experiments that like charges attract each other. Unlike charges, yes, attract each other, and like charges repel each other. Okay, now we need to understand how charges appear, okay, when we disturb the matter. Okay, in the first activity that we discussed in the scale, when we rubbed it, it acquired charge. Okay, so what is the reason of this appearance of the charge? Okay, so this matter, if we just consider, it is ultimately made up of what? Atoms, right? Okay, and inside the atoms what we have neutrons, nucleus. Inside the nucleus we have neutrons and protons. Protons are positively charged, neutrons are neutral. Okay, and electrons, which are negatively charged, they move around this nucleus in this nearly elliptical orbit that we all know. Okay, and they are moving around this nucleus because of electrostatic attraction. Okay, they are bound to the nucleus by some force of attraction. Okay, if this electrons gain some energy, the bond will break. Okay, and it will be free to move. Okay, so here when we are rubbing, what happens? There is friction. Okay, and friction is what kind of force? It is dissipative force. Dissipative means some amount of energy will get lost as heat energy. Okay, so here when we are rubbing, because of friction, some amount of heat is produced, heat energy. That means this electron will acquire some heat energy. That means some energy will be given to it, and it will have enough energy to break the bond with other electrons and with the nucleus, and it will be free to move. Okay, that means now it will give out this electron. Suppose now if we take first matter, this is the atom of first matter, this is the atom of second matter, which are rubbing. Okay, there is friction occurring among them. Okay, suppose the first electron is losing electron to the second atom. Okay, so here initially this atom is electrically neutral. Suppose it has 6 number of protons and 6 number of neutrons and 6 number of electrons. It is losing 1 electron. That means now there is deficit of 1 electron. Okay, that means there is 1 excess of positive charge. So it has acquired, we say that this body has acquired positive charge. When the body loses an electron, it becomes positively charged. Okay, and when it loses 1 electron, the amount of charge of 1 electron is minus E. So it is losing 1 electron. There is deficit of 1 electron. It is acquiring positive charge. There is 1 excess of positive charge, that is positive charge of proton, and we write it as plus E. Okay, and the second atom is acquiring this electron. Suppose the second atom has 5 number of protons and 5 number of electrons. So when it gains 1 electron, there is excess of negative charge. So we called it to be negatively charged. Okay, so when it acquires negative charge, it becomes negatively charged. And what is the charge presented? It will be minus E. Okay, so this is how charges develop in the body because of friction. Okay, one body loses electron, other body acquires electron. The body which loses electron becomes positively charged, and the body which gains electron, it has 1 excess of negative charge. So here it becomes negatively charged. So this is the explanation, that is the electronic theory of frictional electricity. Okay, till now we have discussed that charges apply attractive force among themselves. We have discussed charges apply repulsive force among themselves, right? Okay, but in the activity that we have seen, scale has negative charge because of rubbing. It is attracting paper. Paper was initially uncharged. That means it is attracting uncharged body even. Okay, so how can a charged body attract uncharged body? Let's try to understand it, okay, by the experiment here. When we bring this charged rod which is negatively charged near the metallic sphere which is neutral before, that means it has same number of positive charge and say equal number of negative charge, so that the net charge in it is 0. Initially it is electrically neutral. Okay, so when we are bringing this charged rod near to it, what is the property? It will attract the opposite charge and it will repel the like charge. That means all the negative charges present here will be repelled away. So here it will move far away from this region, so that this region which is near to this rod becomes positively charged and the region which is far away from this rod becomes negatively charged. That means now this metallic sphere is getting electrified. Okay, it is getting electrified, and this process by which it is getting electrified is called electrostatic induction. Okay, this is how this rod, when it is brought near the neutral object, uncharged object, it will attract it, because here inside the body it will repel the like charge and it will attract the unlike charge near it. Okay, so what we see here, this pair, as a result of which it will move near to the rod. Okay, so from here, suppose if we move this rod away from it, that means there is no connection between this rod and the metallic sphere. That means this rod is taken far away from it. So what we will see is, here this metallic sphere is a conductor. What is the property of the conductor? When they have charges, these charges are free to move. They can easily move freely. So what will happen, after some time these charges will move freely through them, and now they will be uniformly distributed throughout, such that the net charge becomes 0. Okay, so that means there is temporary electrification of the conductor only when the charged body is brought near it. Okay, so this is the definition of electrostatic induction. It is what? The phenomenon of temporary electrification of the conductor. This conductor is getting electrified temporarily when we are bringing the charged body near it, such that the opposite charge, unlike charge, appears at its closer end and the similar charge appears at its farther end in the metallic sphere. Okay, so this is the first part. We have understood how the charged body attracts uncharged body with the help of electrostatic induction. Okay, now we will discuss how we can charge a body with the help of the electrostatic induction permanently. Okay, before we had discussed it was charging the conductor temporarily, right? Okay, so now after this second step, what we will do is, when the rod is near to it only, what we will do is we will ground this part of the sphere. Okay, grounding means we will attach this part with the conducting wire, through the wire to the earth. Okay, earth is huge, right? It has huge amount of positive and negative charge, even if we and it is electrically neutral. Okay, if we supply small amount of positive charge to the earth, still it will remain neutral. Even if we supply some amount of negative charge to it, even earth's charge will be neutral. It is like to a sea, if we take out 1 bucket of water, it will not make any difference to its amount of water. It's like that. Okay, so here we are connecting one end which is negatively charged to the ground. Okay, so when we are connecting it to the ground, here wire being a good conductor, it will conduct the negative charge to the ground. Okay, so now it only has the positive charge in this region. Now in the last step, what we will do is we will move this rod away from the spare. Okay, so now the property of the conductor being free charges, they can move freely through them, so this positive charges will be uniformly distributed. Okay, so now this metallic sphere is positively charged. Okay, so this is how we can charge the body with the help of electrostatic induction. Okay, so till now we have studied about charges. Okay, now how to find out the given body has charge or not. Okay, to find out we will use the instrument which is called gold leaf electroscope. Okay, let's see how it looks like. Here in the diagram we have the instrument. Inside the instrument what we have, one rod which is connected to the bulb. Okay, and to the end of this rod we have connected very thin foil. Okay, thin foil, two foils which are pressed together. Actually initially these two foils are together, it's like this, two papers or two copies, very thin, which are kept together. Okay, initially they are kept like this. Okay, now we will bring a charged body near to this metallic bulb. Okay, suppose it is negatively charged. Okay, and this bulb and the rod, it is made up of a conductor, right? It is a good conductor of electricity. Charges can flow through them easily. So what will happen, the negative charges present in it will flow through this thin wire, and this gold foils will acquire negative charges. Both of this gold foil will acquire negative charge. Initially they are like this together. Okay, thin foils together, both have same kind of charge, that is negative and negative. What is the property? Negative charges repel each other. So what we will see is these two foils will diverge away from each other like this, as shown in the diagram here in the figure. Okay, so there is divergence in the leaves, gold leaves. Okay, because both of them acquire same kind of charge. Okay, so by seeing the divergence we can say that the body which is brought near is a charged body. Okay, and here if the charge is more, the divergence here produced will be more and more. That means this gold leaves will move more and more away from each other. Clear? Okay, so this is how we detect and measure charges with the help of gold leaf electroscope. Okay, we have already seen in the various activities what are conductors. Conductors are the substances through which electric charges can flow easily. If we supply some charge to the conductor, after some time it will be uniformly distributed. Okay, that is the property of conductor. Whereas insulators are what? They are the substances through which charges cannot flow easily. Okay, so if we supply some amount of charge to the insulator, they will remain as it is. That means the charges will remain accumulated in the same region, as they cannot flow through them easily. Okay, examples are glass, wood, plastic, etc. Right? Okay, now next thing that we have to discuss about the charges is the basic properties of electric charges. Okay, so if we consider one system. Okay, this is our system. To this system, inside the system we have different charges, Q1, Q2 and Q3. Okay, and now we want to find out what is the total charge. Okay, so total charge in the system will be the sum, addition of all these charges which are present inside this system. Okay, that means charges can be added. So this is the property, first property of the electric charge, that is additivity of electric charge. That means total charge of a system is the algebraic sum of all the individual charges located at different points inside the system. Okay, let's consider the second example. Suppose this is our system and we have inside the system one charge plus 1, second charge minus 2 q2, and the third charge plus q3. So now the total charge will be q1 minus q2 plus q3. That means the charges will get added. Okay, so this is the first property. Hope I am clear. Okay, now let's discuss the second property, that is called quantization of electric charge. First we need to understand what do we mean by quantization. For that we will take the simple example. Okay, in the container, two containers, if we consider, in first container we have water, in the second container we have hailstones. Okay, if you want to transfer this water, we can move the water by any amount. Okay, but if you want to move these hailstones, we have to move it one by one. That means we can count it and move it. Likewise, electrons or the charges, they are also quantized. They are present in the form of the packets. Okay, they can be counted, okay, as some finite number of charges, and when we are transferring charge from one body to another body, they are also transferred as some number of the charges. Okay, so here suppose in this body we have n number of charges and each charge has the amount E. So total charge will be n into E. Okay, and n is what? Integer. Integer means it can have the value 0, plus 1, minus 1, plus 2. When we have positive charge it will be plus, when we have negative charge it will be minus. Okay, but we cannot have half of E. We cannot transfer half of the charge. Okay, like we cannot transfer half of the hailstone. We cannot, we have to take it as a whole. Okay, so here total charge of the body is always an integral multiple of basic quantum of charge, that is Q is equals to NE. Quantum means like a packet of charge. Okay, clear? So this is the second property. Now the third property is charges are conserved. Okay, what do you mean by that? If we have, for example, suppose sodium and chlorine. Okay, initially they are neutral. When sodium loses one electron, it becomes positive, and when chlorine gains one electron it becomes negative. Okay, so now they are charged. Initially their net charge was 0, they were uncharged. Now we are transferring negative charge from sodium to chlorine. Okay, we are transferring, we are not creating the charge, we are transferring, which was already present in the sodium, we are transferring that charge to the chlorine. Okay, now as the sodium atom is losing one electron, the charge acquired by the sodium will be plus E. Okay, and as there is one deficit of negative charge, and here chlorine acquires this electron, that means there is excess of electron, the charge acquired by it will be minus E. Now what will be the total charge? Total charge will be plus E minus E, that will be 0. Okay, so here even after the transfer of charge, even net charge is 0. That means initially net charge was 0 when sodium and chlorine was uncharged, and finally even after the transfer of charges, net charge is 0. Okay, so here the law of conservation of charge says electric charges can neither be created nor be destroyed, but they can only be transferred from one body to another body. Hope I am clear with this example. Okay, now let's take another example. Here, same as in the activity scale, when we are rubbing it with the hair, scale acquires negative charge, hair acquires equal amount of positive charge. Initially both are uncharged, net charge is 0. Finally, suppose the scale acquires minus q charge, hair will acquire equal amount of positive charge. Again net charge will be 0. Okay, so here also net charge is conserved. The net charge before and after the transfer is 0. Okay, so this is the third property of the charges. So we have discussed the three property of the charges. First property was charges can be added in the system. Total charges sum of all. Second is charges are quantized. We can write the total charge as the integral multiple of the charge, that is E, charge of electron, and the value of charge of electron is 1.6 into 10 to the power minus 19 coulomb. Coulomb is the unit of charge which we will discuss afterwards in detail. Okay, now let's go to the Coulomb's law. Okay, what is law? The Coulomb's law here. For that, we'll consider two charges Q1 and Q2. They are separated by the distance R. Okay, they are separated by the distance R. These charges are called point charges. That means the size of this charge is very small in comparison to the distance between them, so that its size can be neglected. Okay, so we are taking point charges. Okay, and we know that there is some force of attraction or repulsion between the charges. Now what is the amount of force acting between them? That force was given by Coulomb's law. According to him, what was the force between them? Force is directly proportional to the product of the charges. Okay, first charge is Q1, second charge is Q2, and the force is inversely proportional to square of the distance between them. Let's recall the gravitational force of attraction. It was what? It was proportional to the product of the masses and inversely proportional to square of the distance between them. Okay, here also the force of attraction or repulsion. We know that there is attraction between charges and there is even repulsion between the charges depending on the kind of charge. Okay, the force of attraction or repulsion acting between the charges is directly proportional to the product of the charges and inversely proportional to square of the distance between them. Okay, now let's combine these two. What will obtain? Force is proportional to Q1 Q2 by R square. Okay, now let's remove the proportionality sign. When we remove the proportionality sign, what will gain? We'll have here a constant of proportionality which is K into Q1 Q2 by R square. Okay, this K is the constant of proportionality. Okay, now this constant, actually this constant, it is not the same in all the medium. Okay, now if we take these two charges in air and again we will take these two charges, suppose we immerse these two charges inside water. Okay, then in these two cases, the value of this constant of proportionality will be different. Okay, so this constant depends on the media, okay, medium between in which the charges are placed, okay, and its value also depends on the type of system used. We use CGS and SI system. In CGS system, the value of K is 1. So in CGS, this force will be Q1 Q2 by R square, whereas in SI system, the value of K is 1 by 4 pi epsilon naught. Here, if we consider the medium to be vacuum, we have discussed this K depends on the medium. Let's start with the simplified one. We'll take the medium to be vacuum. Okay, so here in this case, this constant of proportionality will be 1 by 4 pi epsilon. This is Greek letter epsilon with the 0 not here. Not stands for the medium vacuum. Okay, this epsilon naught is called permittivity of the medium. Okay, by the value of this permittivity, we can find out what amount of forces will be acting between the charges placed in that medium. That means this is the property of the medium which determines the amount of force acting between the charges. We'll discuss about this permittivity in detail again afterwards. Okay, let's first discuss this force. Okay, so here this force is equals to 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay, now what is the case if we take any other medium? Okay, in any other medium, suppose the permittivity is epsilon only. In that case, the force will be 1 by 4 pi epsilon Q1 Q2 by R square. Okay, now what is the value of epsilon naught? This is the property of the vacuum and it has a particular value number. Okay, the value of epsilon naught is, it has value 8.85. I remember the value only up to 2 decimal numbers into 10 to the power minus 12. Okay, now this is the value of epsilon naught. What is its unit? Okay, so for the unit, let's see, but before that, let's erase this all. F was 1 by 4 pi epsilon naught Q1 Q2 by R square. So from here, what is the unit of force? Newton. We want to find out the unit of epsilon naught. 4 pi is a constant. What is the unit of Q1? That is coulomb, into unit of charge, that is coulomb. So it will be C square by unit of R is meter, that is meter square. So the unit of epsilon naught will be, taking this to the left hand side, what will have? Coulomb square per meter square, which we can write as meter to the power minus 2. Newton goes to the denominator, that is Newton to the power minus 1. Okay, so this is the unit of epsilon naught and its value is 8.85 into 10 to the power minus 12. C square meters to the power minus 2 n to the power minus 1. Okay, so when we are doing the numericals, we'll put the values of the charges given and the distance between them, and by putting the value of epsilon naught, we can find out what is F. Okay, or we can simplify this. You can calculate this value and find out that 1 by 4 pi epsilon naught is 9 into 10 to the power 9. Okay, so we can directly put this value when we are solving the numericals. Okay, and its unit is the inverse of this, that is Newton meter square per coulomb square. Okay, this is Coulomb's law. I hope I am clear. Okay, this gives the force of attraction or repulsion between the point charges which are at rest. These 2 point charges are at rest, and it is directly proportional to the product of the charges and inversely proportional to square of the distance between them. Okay, and now here see, suppose this is positive, this is positive. That means now Q2 will be repelled away from Q1. So the force acting on it will be acting in this direction. That means force will be acting along the line which is used to join this two, Q1 and Q2. So force will be acting along the line joining these 2 point charges. Okay, now force on Q1, that is now force on Q1 due to Q2. Q1 will be repelled away. So this is the direction of the force acting on Q1. So again it is along the line joining the 2 charges. Okay, direction will depend on the kind of charge, positive or negative, that we have taken. Okay, this is Coulomb's law. Now in this expression we had discussed that F is 1 by 4 pi epsilon naught Q1 Q2 by R square, and in this expression we had taken the charge, the SI unit of charge, to be coulomb. Okay, now we have to find out what is the value of this 1 coulomb. Okay, this is the SI unit of charge. Now let's define what is this 1 coulomb. Okay, so to find out its value, the amount of the charge present in 1 coulomb, we will use this expression. Okay, now when Q1 is equals to Q2 is equals to 1 coulomb, okay, we are taking the point charges to be 1 coulomb each. Suppose the distance between them is 1 meter. R is 1 meter. Then what will be the force acting between them? Force will be 1 by 4 pi epsilon naught is what? 9 into 10 to the power 9. Here Q1 into Q2 is 1 into 1 by R square is 1 square because it is 1 meter. So here what is the SI unit of force? That is Newton. So what we acquire here is, when we take 2 charges of amount 1 coulomb separated by 1 meter, the force of repulsion, here we have taken positive charge, that means they will repel away. Okay, they will repel each other. The force of repulsion acting between them will be 9 into 10 to the power 9 Newton. From this we can define 1 coulomb. Okay, so 1 coulomb is what? It is that amount of charge which will repel equal and similar charge with what amount of force? With force of 9 into 10 to the power 9 when it is placed in vacuum, and the distance between them is 1 meter. Okay, that is the definition of 1 coulomb. So see here, what is 1 coulomb? 1 coulomb is that amount of charge that repels equal and similar charge with a force of 9 into 10 to the power 9 Newton when placed in vacuum at a distance of 1 meter from it. Okay. Now let's see its CGS unit. CGS unit of charges. First we'll see electrostatic unit of charge. Okay, ESU means electrostatic unit of charge, or stat coulomb is the CGS unit. Okay, and the relation between 1 coulomb and the ESU of charge is here. 1 coulomb is 3 into 10 to the power 9 ESU of charge. Now to define this ESU of charge, I'll leave it to you. How we'll do? Here in this case, we'll take 2 point charges of 1 ESU of charge. they will be separated by 1 centimeter. Then force will be 1 by 4 pi epsilon naught q1 q2 by r square. What is this k, constant of proportionality in CGS? It will be 1 into q1 q2 is 1 ESU, 1 into 1 by r square. So here r is 1, so again this will be 1 square. So force will be 1. What is the CGS unit of force? It is dyne. So here the force acting between these two ESU of charges will be 1 dyne. From this information, please define what ESU of charge or start coulomb is. Okay, I'll leave this to you. Okay, we'll discuss till here. Hope you have understood what I have taught. Please like and subscribe to this channel. In the next class, we'll discuss with the vector form of the Coulomb's law.